All right, good afternoon and welcome everyone to today's AllTranstek webinar titled Welding, Are You Compliant? I am Todd Tranowski, Senior Transportation Analyst with FTR, and I'll be your moderator for today's webinar. Compliance with welding regulations is critical for railcar facilities and welding personnel. The webinar today, we hope to help you learn about the scope of work as it relates to facility certifications, tank car tank welding, and other railcar welding. This webinar will really focus on the procedure specifications and welder performance qualifications that everyone needs to be aware of. We're delighted you're able to join us today for this webinar. As a bit of house cleaning, I want to let you know that there will be a webinar replay available later this week or early next week. An email reminder will be sent out once the replay has been posted. The format for today's webinar will be formal remarks from our speakers, followed by a question and answer session. The length of today's webinar is scheduled for 1 hour. All of the formal remarks should be completed within 45 minutes to allow us for approximately 15 minutes of questions and answers. If you type your question and answers in, they will show up in a box to me, and we will go through them at the end of the webinar. But now let's move on to the formal presentation. Joining me today are two distinguished professionals in the welding field. We've got Steve McCullough, the Director of Welding and Special Processes with AllTranstek, and Mike Untermeyer, the Welding Engineering and Special Processes Consultant over at AllTranstek. Both of these gentlemen have over 30 years of experience in welding, focused on different areas with particularly non-destructive testing, quality assurance, and engineering. They've been in various different training programs, certification programs, and program development. Steve belongs to several industry organizations and holds certifications in various states and various areas for welding programs. And Mike has similar qualifications, including experience with tank car regulatory requirements, tank car repair, design, failure analysis, and metallurgical concerns such as corrosion and fatigue cracking. He is chair of the Association of American Railroads Welding Task Force and has been published in the Welding Journal. Without any further ado, gentlemen, please take it away.
Welcome, everybody. This is Steve McCullough. I'm going to get us started here. Just give me 1 second for it to transfer over. Not transferring. Okay, so what we're going to cover today is we're going to go through a little bit about a scope of work as far as facility certifications. We have a section we're going to talk about the welding procedures. We're really going to focus on the codes that we follow in the railroad industry, Appendix W and the AWS D15-1. We'll get into the actual procedure qualification record, what's all involved in it. We'll talk a little bit about pre-qualified welding procedures, some welding compliance. And then the last half of the section, we're really going to kind of go into welder performance qualification. A little bit about AllTranstek. Who are we? What are we? We're basically a fleet management company. We manage about 275,000 rail cars. We also have our service group, our technical services group, where we get involved in regulatory compliance, welding, NDT inspections, and then we also have our basically what our strategic services group does, provides 360 overview of railroad supply chains. And this kind of just breaks down, we're kind of broken up into 4 main departments. We have our fleet management group that really manages the 275,000 rail cars. We have our client services group, gets into auditing, rail car maintenance management, tracking. We have our technical service group, which I talked about, where we do railcar inspections, regulatory, essential watch, non-destructive testing, engineering, and then our strategic planning group that does planning, market size segments. So that's really what AllTranstek does. And this is really, Mike and I both work in the NDT and Special Process Department. This is just our group. What we're any of our guys come out to your facilities just to kind of show you who we are and what we look like if we come to your facility. So I'm going to hand it over to Mike. He's going to go through the scope of work and welding procedure section.
Okay, good afternoon, everybody. Thank you for joining us. The first slide up here you see is some various facility certification codes. And what we're trying to do is, if we're asked to develop a welding procedure, or you need to develop a welding procedure for your particular operation, the first thing that needs to be done is to identify your scope of work. Will you be welding on tank car tanks, or will it be some other welding? And so these are just some examples of various codes that Appendix B has for particular scopes of work. Okay, once we've identified your scope of work, now, as Steve mentioned, we have two particular specifications that we normally work with in this industry. One is the AAR MSRP C3 Appendix W. Appendix R would actually be the repair, but for purposes of welding procedure qualification and performance qualification, R refers to W. So this is the specification we would use if we're going to weld on a tank car tank. For other welding, jacket welding, hopper car welding, any other welding other than the tank car tank itself, we'll use AWS D15-1, and the title of that is Railroad Welding Specification for Cars and Locomotives. So we have to decide which of these particular specifications we'll use based on our scope of work. Okay, now some examples of what we're going to show you in the next few slides are some examples of welds that would be covered under these different welding specifications. Here we see a side sheet on a hopper car, and that particular weld, fillet weld, would be covered by AWS D15-1 specification. Okay, now this slide is similar to the slide on the hopper car, but this is a tank jacket weld, and that again would be covered by AWS D15-1. Another jacket weld where we have a ladder support welded to a jacket, fillet weld there, again covered by AWS D15-1. And this is a bolster pad to a tank. So now we're welding on the tank car tank proper, and so now we'll switch to a different welding specification. That particular fillet weld would be covered by Appendix W. And here we have two examples of welds of bottom reinforcing pad to the tank, and that fillet weld would be covered by Appendix W, governed by Appendix W. And then we have a portion of a draft seal transition pad there that's welded to the reinforcing pad itself. And because it's welded not to the tank, it's welded to the reinforcing pad, that particular weld would be covered by AWS D15-1. Here we have a bottom valve on the tank car, and we see fillet welds there. It could be groove welds too. Groove welds and fillet welds on the steam jacket, again covered by AWS D15-1 because it's not part of the tank car tank. And then we have some induction pipes, maybe a gauging device, thermal well, sample line that are welded to the bottom of fittings flange. And again, because it's not part of the tank car tank by definition, these particular welds will be governed by AWS D15-1. Okay, here we have a head shoe reinforcing pad and the head brace itself. Because the head brace reinforcing pad is welded directly to the tank car tank, that particular weld is governed by Appendix W. And then, of course, the head brace itself, which is welded to the draft seal and to the reinforcing pad, and since those members are not part of the tank car tank, those welds will be governed by AWS D15-1. Example of a fluid manway. And this will be a recent change here. Any butt joint or any weld joint on the nozzle itself will be governed by Appendix W. And part of the reason for that is that the federal government and the Tank Car Committee have determined that because AWS D15.1 is not currently incorporated directly incorporated by reference into the federal regulations, that the tank car nozzle and nozzle to flange welds will have to be covered by Appendix W. Okay, the fluid nozzle, this is just a different, instead of a groove weld here, we have a fillet weld where the nozzle is actually fillet welded to the flue. And then probably we have a fillet weld where the nozzle is welded to the flange. And again, those welds will be covered by Appendix W. And of course, the inserted manway, which is the groove weld into the tank shell, that weld has always been covered by Appendix W, the nozzle to tank shell weld. Okay, again, one of the things that we have to identify under your scope of work is what material will be welded. Will it be carbon steel? Will it be stainless steel? Will it be aluminum? Of course, we could have castings, AAR M201, various grades of castings, which bottom outlet saddles and a lot of the running parts of a truck are made out of. And then, of course, the ASTM CF8M or CF3M, which is stainless steel castings. The point here, we have to clearly identify what materials are being used. And how can we do that? Some of these materials will be identified through ASTM standards. There's Appendix M in the C3 AAR specification as a listing of materials for both tank proper, and then for other items as nozzles and flanges, and there's a pretty comprehensive list in Appendix M. There's also a document put out by AWS. It's called the base metal grouping. It's the number is B2.1, and there are a whole host of materials identified: aluminum, stainless steel, carbon steel, and they're identified by M numbers and group numbers. And the purpose of grouping materials is to decrease the number of required welding procedures. Materials are grouped by their mechanical properties, the tensile strength, corrosion resistance or yield strength, what's the chemistry. That's the reason for grouping these materials, both under AWS B21 and also in ASME Section 9. We have the same system with P numbers and group numbers. And in almost all cases, an M number identified by AWS specifications will be the same as a P number identified in the ASME material grouping. In other words, if we have an example of that would be 51670 material. It's considered a P1 material in the ASME Section 9 system, and it's considered an M1 material in the AWS base metal grouping. So usually the P number will correspond with the M number. And then group numbers are typically only used when notch toughness requirements are imposed. If we have notch toughness properties or requirements imposed on the weld procedure, then the grouping has to be further limited. It can't just be an M1 group. We have to look at the group number. And so if I qualify a procedure without notch toughness and it's an M1 grouping or a P1 grouping, then I should be able to use that procedure for welding any M1 and any P1 material together. Now, if I have notch toughness requirements, then I have to look at grouping. What is the group number? That further limits the use of my use of possible materials if I have notch toughness requirements. So clearly identifying what materials we have to weld on, we have to do that as a part of this identifying the scope of work. Okay, and the next thing would be what welding process will we use? And we have 5 identified up here: shielded metal arc welding, of course, flux core arc welding, gas metal arc welding. Could be any one of these 5 or all in case of maybe a major manufacturing operation might use all of these. Or if it's maybe a valve manufacturer would be using gas metal arc and gas tungsten arc welding. So we need to identify the welding process, and some things to know about particular welding processes is, say for instance, flux core welding. Those electrodes are identified by an F number, and that particular F number is F6. So if I have a process, flux core arc welding, from the standpoint of F numbers, I can use any F6 electrode when I'm qualifying a procedure, just looking at that for an essential variable. Under gas metal arc welding, metal core arc welding is included in that. And then for submerged arc welding, we'll have to look at the AWS flux wire classification to determine whether we have adequate tensile strength in the filler metal, if we expect it to meet the required notch toughness properties. That's the classification for the submerged arc electrodes and fluxes. And then one thing that some people have had problems with gas tungsten arc welding is the addition or deletion of filler metal, which is an essential variable for qualification under those under that welding process. In other words, if you qualify with filler metal and you try to use this as a process without filler metal, then that has to be qualified separately, because that is an essential variable. Okay, so if we're looking at qualified procedures, if we're using Appendix W, there is no provision for pre-qualified procedures as there is with AWS D15.1 specification and other AWS specifications. Excuse me. So we don't have a choice. We have to qualify procedures if we're welding on tank car tanks. If we're welding in other areas, jacket welding, structural welding, we have the possibility, and again I use the term possibility, of using a pre-qualified procedure. We have to look at all the requirements that are in D15.1 for pre-qualified procedures and make sure that we're able to use a pre-qualified procedure. And if we don't meet all those requirements that are listed, then we have no alternative but to qualify the procedure. So once we identify whether we have to have a pre-qualified procedure, if we can use one, if we can, then we can eliminate the mechanical testing. If we can't use a pre-qualified procedure, then of course we have to first weld test coupons that will be mechanically tested, and that will of course lead to our procedure qualification record, the results of the mechanical tests. And once we have that, then we can establish our welding procedure specification. Okay, for now, if we're looking at a qualified procedure, we have to answer the question, what joints need to be welded? Is it a groove weld? And if do we have to do a groove weld, or can we get by with a fillet weld? Typically, groove weld qualification will qualify fillet welds, but not vice versa. And if we do have a groove weld, we have to ask ourselves, does that weld have to be a complete joint penetration, CJP abbreviation up there for it, or are we looking at a partial joint penetration? You might ask, well, what are examples of partial joint penetration welds? In some cases, the tank nozzle to the nozzle flange in some designs is a partial penetration weld. So we have to do something a little bit different with partial penetration welds as opposed to a complete penetration weld. And what mechanical testing is required? Of course, with groove welds, typically tensile tests and guided bend tests are required to qualify that particular joint. If we're doing a partial penetration weld, then we're looking at doing a macro etch. And some of you may be asking, well, what is that exactly? We'll give an example of that in some slides that are upcoming here. But if we do a partial penetration weld, we have to do a macro etch to show or demonstrate how much penetration we actually have in that particular joint. So if the weld procedure calls for 70% penetration, on our welding symbol calls for that, then we have to establish that we actually do get 70% penetration with a particular weld. It's okay to overshoot that, but we have to have that as a minimum. And we have to, the way that we'll establish that is with a macro etch, and look at the cross section of the weld and make sure that we have at least whatever specified amount of penetration is required. Corrosion testing, that's required if we have corrosive commodities to be hauled in a tank car tank, or excuse me, if we're exposing a valve to a corrosive commodity, or a sipon pipe, or anything, thermal weld, magnetic gauging device. All those, any weld there would have to be corrosion tested. Now, excuse me, if we're looking at pressure car tanks, there are two other things that we have to do. We have to do hardness testing on the heat affected zone and the weld metal, and we also have to do notch toughness testing. And that's any pressure car that we might weld on is going to require a weld procedure qualified with notch toughness values. Okay, here's an example or a picture of on the left of a typical tensile test machine. And then on the right, we have a reduced section tensile specimen outlined. And so for the usual requirement for a welding procedure qualification is to have two tensile tests pulled. And of course, the weld, which is shown in the dark area on the right side on the drawing, you can see how that specimen is reduced in the center. And the reason for doing that is we want to make it fail preferentially in that area. We don't want it to fail somewhere outside of that area. So the tensile strength would have to be at least that of the base metal. So that's a requirement for the reduced section tensile. Okay, and also another requirement mostly for groove weld procedures is guided bend tests, and most of the time 4 side bends are required, or 2 face bends or 2 root bends are required on thinner material. As an example, if I'm going to weld a 1/4 inch thick material, I probably would not cut a side bend specimen from that for procedure qualification. I would bend the face of the weld and the root of the weld instead. 2 face bends, 2 root bends instead of 4 side bends. And a point I should make about the plunger, which you can see the rounded part that is pushing down on the bend specimen, that plunger has different diameters for different types of material. If we're welding some high strength material, or we're welding some aluminum, the higher strength aluminums, then typically the diameter of that plunger will increase, because if we try to bend it at too sharp of a radius, it will fracture just because of the material properties. So that plunger diameter is not always the same. So if you're going to weld higher strength materials or certain aluminum alloys, you need to check what plunger diameter is required, and typically if you're sending specimens out to a lab for testing, they will do that as long as they know what material it is. Okay, we mentioned macro etch earlier. This is an example. This is not an example of a partial pen weld. This is a full penetration weld into a backing, and this is the macro etch, and I'm not so sure that you're able to see it, but there are some small dots in 3 areas on that particular specimen, down toward the bottom. You can see it in the heat affected zone and across the weld, and then through the middle of the weld, and then also close to the surface of that weld. Those are micro hardness readings taken by the test lab. So that's an example of what that would look like if you were looking at cross section. Okay, this is a similar macro etch, but this weld has been this is a double weld. It's not welded from one side, but again, you can see the multiple passes of the weld of the weld made from one side, and then multiple passes on the other side. And you can also see the little white indentations there, which are micro hardness tests in the weld metal and heat affected zone. So this is kind of what a macro etch would look like. Okay, we mentioned the requirement for notch toughness testing. This is not the only way to test this, but the typical way that we would test notch toughness is with the Sharpie V-notch test. And at the upper left-hand corner, you see the actual impact testing setup. And if you look at the right of that picture, you see what's called a hammer, and it's brought up into the loaded position. And that hammer will actually be released, and it will strike the impact specimen with a certain force. And the force that it takes to break that particular Sharpie specimen is measured in foot-pounds. And of course, the more foot-pounds that we have during a break test like that, then the more impact resistance we have. And in the upper right-hand corner, you see the typical Sharpie specimen, and usually it's a little bit over 3/8 of an inch as a square. It's the typical dimension is 0.394 by 394, and then the notch itself, which is seen in the upper view, that's machined to very precise specifications also. And so that's the notch initiation point for the fracture of a Sharpie specimen, and then we'll measure the foot-pounds and see how much energy is required to break it. And then in the lower right-hand corner, you see 2 types of fracture. The one on the left is a brittle fracture, which is usually undesirable because that means there was very little energy taken to break that particular specimen. The specimen on the right is referred to as a cup and cone fracture, which is more of a ductile fracture. And you may be saying, well, what does all this have to do, and why does this really matter? As I mentioned earlier, the impact test is a measurement of energy that it takes to break this specimen, and with tank car tanks or any structures for that matter, if the car is in a collision or derailment, we don't want the tank to be breaking open in a brittle fashion and releasing commodity. We expect the tank to bend and buckle and deform and absorb energy, but we don't want it to break and spill the commodity. So that's the reason for the requirement for notch toughness. Okay, so after we've welded the coupon and tested it, now we have to put together our procedure qualification records, and usually welding position only comes into play when we have notch toughness requirements. And if the reason I say that is if I don't have any notch toughness requirements specified, if I weld that coupon in the overhead position or the down flat position or the horizontal position, doesn't really matter. The side bends or the testing of the side bends or the tensile test will not really be affected adversely by one position or the other. However, if I'm going to weld a test coupon and I do have notch toughness properties specified, then typically most codes say that if I weld that coupon in the vertical up position, that's the most severe case for notch toughness. Why is that? Because that's the most heat input, the slowest travel speed, and the most severe condition that we would see in a production environment. So if I qualify in the 3G up position with notch toughness requirements, then I can weld in any position per the procedure, simply because heat input has an adverse effect generally on notch toughness properties. Post-weld heat treat obviously is an essential variable. We have to qualify a procedure. If we don't use post-weld heat treat, if it's just the procedures used in the as welded condition, and we add post-weld heat treat, it has to be qualified with that post-weld heat treat. Now in Appendix R and also Appendix W, we have an option to use a 300-degree minimum preheat in some cases in lieu of post-weld heat treat, and that's actually mostly for repair of tank cars, as specified in paragraph R24, I believe, of Appendix R. So in some cases, this is not for pressure cars, but in some cases on GP cars, we can use the 300-degree preheat in lieu of post-weld heat treat. However, we have to control our we have to control our preheat or qualify the procedure with that preheat. And then, of course, with notch toughness requirements, we have to measure the heat input and when we qualify the welding procedure, and then we can't exceed that heat input. And the formula there would be amps times volts times 60 divided by your travel speed, and that's a formula that would be used to calculate heat input. Okay, an example of a procedure qualification record, and what would be in here is the results of our tensile test, the results of our bend tests, our corrosion tests, and then we would have notch toughness values specified here, and who welded the coupon, that sort of thing, where it was tested. So this is an example of a PQR procedure qualification record. Okay, welding procedures. If now we've got a PQR established and we have to do a welding procedure, we have to list obviously all the essential variables, and these are some examples: wire feed speed, your electrode specification, the base metal limitations, and that gets back to M numbers, P numbers, and group numbers, what kinds of joints will be used, amperage and voltage, specified as a range and travel speed also. And then for notch toughness, what was the maximum heat input that was used to qualify the procedure. An example of a welding procedure specification, and this would again have more of the ranges, allowable ranges of materials and amperage, voltage, travel speed, joint designs. This is just an example. They can follow many different formats as long as all the required information is put down in the procedure specification. Okay, that's pre-qualified welding procedure. This is where you know, we can't just say that I have D15-1 in my bookcase and therefore I have a pre-qualified welding procedure. That's not allowed. We still have to qualify or have documentation for the pre-qualified procedure. And we have to meet all the pertinent requirements of AWS D15-1. That's clauses 5, 6, 7, and 8. And some procedures that cannot be pre-qualified is if we're going to have post-weld heat treat, if we have gas metal arc welding with a short circuiting transfer, if we're welding vertical down, that's not allowed to be pre-qualified. And in D15-1, stainless steel material and aluminum material cannot be pre-qualified. We have to develop a qualified welding procedure for those materials. Okay, and here's an example of a pre-qualified welding procedure, and there are pre-qualified joints listed in AWS D15-1. Other AWS codes that recognize pre-qualified joints, those joints will be listed there as well. But those joints are very conservative, and you can't, as long as you comply with the joints that are listed in D15-1, then you can use that pre-qualified welding procedure. Okay, and we do have to look in some other standards for welding requirements. Everything is not nailed down in D15-1 or Appendix W. Sometimes we have to look at the field manual for ways to repair a draft seal. S402 for brake pipe welding. There are some requirements in there that are a little more stringent than D15-1. And then, of course, some of the AAR standards with couplers and yokes and truck details, they have certain specifications on what can be welded where and how much buildup can be put down. And again, this list is not all inclusive, but this is just to point out that we have to look in other AAR specifications, sometimes in the federal regulations too, if we have particular low temperature commodities, 179, 102, I believe it is, that gives us some additional Sharpie notch toughness requirements for a welding procedure. So there are other sources that we have to check out if we're going to qualify a welding procedure.
Okay, so once welding compliance, Mike's went over a bunch of stuff with welding procedures, whether you're Appendix W, D15-1, and then additional requirements. So at that point, the welder's completed a coupon, so basically you would have somebody at your company weld a test coupon, and you do all the testing. So technically at that point, you really only have that person certified. Nobody else really at your facility can weld. He can only really weld within the position that he welded. So as Mike said, some welding procedures we can qualify flat. So this welder would only be able to weld with that procedure in the flat position. And remember, procedure qualification is a starting point. Welder qualification or welder certification is ongoing. You'll spend time developing a welding procedure, but once that's in place, the bulk of your time is going to be spent certifying and qualifying welders to make sure they're compliant to weld with those procedures. So welders cannot be pre-qualified. And also one thing is a welder that's been certified at one facility cannot be transferred to another facility. The next question we have to determine is, are we going to do a groove weld, fillet weld, performance qualification test? And then the position becomes very important. What position they're going to weld with and what process. Like Mike talked about earlier, the different welding process. I have a slide that talks a little bit about that. Then we get into the essential variables. What am I qualified to weld? So you can give a welder a test, but what does that test really cover? So we need to know what F number they're certified to, what the base metal was it ferrous, non-ferrous, what welding process, as we get into gas metal arc, shielded metal arc, flux core, and I have some slides on that, what position, and then whether they welded with a backing or the omission of a backing. And, Mike also listed gas tungsten arc. This one I just listed the 4 major ones. Like I said, gas tungsten arc is used in our industry, but the bulk of tanks are welded with these 4. So just to kind of show you real quick, shielded metal arc welding, that's what's commonly called stick welding. Then you get into flux core arc welding. It can either be a dual shielded process where I have an external shielding and an internal flux within the wire, or it can be self-shielded flux core where it has no external shielding gas. And then we can have gas metal arc. Gas metal arc is typically when we used to call welding MIG welding. This is what gas metal arc is. It's basically it's a gas does all the shielding, and then it's a solid bare wire. And then we have submerged arc welding. If you've ever seen a tank car, all the big girth seams that are welded is with submerged arc welding. That's where we have a granular flux. That's all the welding takes place. Don't need a welding helmet. It's all done underneath a granular flux. The other thing that becomes really, so my process is very important, and my position becomes very important. So positions, AWS and D15-1, they keep it the same within the industry. They base it on position. So I have 1G, 2G, 3G, and 4G. So 1G is basically flat, 2 is the plate is horizontal, or the welding is progression is horizontal, 3G is vertical up, and then 4G would be overhead. And then the same process would go for fillet welding. So 1F would be a truly flat weld, 2F would be horizontal, 3F would be vertical up, and then 4F would be overhead. And then we get into pipe certification. In some cases they transition across, but in most cases pipe welding, anything under 24-inch diameter would fall under pipe. So we get into 1F, which is a rotated pipe. So the pipe is actually rotating. Your welding will only take place in the flat position on top. 2F would be the plates flat, pipes on top, and then 4F would be overhead, where you're welding overhead the plate, or it could be a socklet weld. And then 5F would be the plates basically vertical, the pipes coming in horizontal, and it's in a fixed position, so you're welding around. I have some pictures. I will show you this. And then the 6G pipe test would be where the pipe is at a 45. That's on the bottom. And again, the pipe is fixed, you're rotating around. The 5G would be the one above, where the pipe is horizontal, rotation, or the progression could be up or down. And then 2G would be the pipe's vertical, welding is basically what they'd say in the horizontal position. And then the 1G at the top would be a rotated, where the pipe is actually rotated. And this slide just those were the ones that we pulled out of the actual code. So you could go to Appendix W and they would show you those. And this just kind of shows you, again, just all broken out in the different positions. So again, 1F is flat, 2F horizontal, 3F, all of them listed. Which it's kind of easy to see these, you see the slides in it, but what I thought would be good is to actually see a welder welding. So this is one of the guys at one of the shops actually taking a flat test, and he's actually welding with flux core. The plate is truly flat, so that would be a 1G test. So then this would be what we'd say 2G. He's at the horizontal position. The guy's welding in the horizontal plane. In this scenario, he's showing you can either push or pull the arc. That's going to change with penetration, but that really gets into technique. And then 3G would be vertical up. So that would be the welder starting at the bottom. Now I could weld vertical up or vertical down. For this, anytime you get into thicker, heavier construction material, you're going to weld vertical up. Vertical down does not give you as much penetration. And then this would actually be, the 4G would be the overhead. So the guy is actually welding across overhead, trying to follow where he's going. And again, all these are the different tests that we give. You give welders, any welder coming in the shop would have to take tests similar to this. And then you could also give him fillet tests depending on what he's welding. So a 1F is truly is flat in that gravity isn't taking place and pulling down to one plate or the other. So you're really truly welding in a V. And that would be actually what we call the 2F, is welding horizontal, and that would be 3F, which would be vertical, and then that would be 4F, welding overhead. And then we showed you the slides on the 5F position, which would be a pipe to a plate. So this would be basically a plate, and the guy's going to weld. He's doing vertical up progression around the plate. He'll weld from one side, and he'll go and weld the other side to get full penetration. And then this is showing you the 6G test, where the pipe's at a 45 degrees. Guys welding vertical up on both sides. Again, if you're going to have guys make repairs on handrails, handrail is a pipe certification, so they would have to take a test similar to this to weld on pipe. So when you go into any of the codes, they're going to list each position that you take, which we just talked about, and they're going to show you an associated position that you're qualified in. So if you take a 1G test, you're going to be qualified for flat, which would be 1G. Appendix W lists a little bit different than D51, but the F under groove would be 1G, and then the F under fillet would be 1F. So, if you ask the question, well, why is it customary to give a welder a 2G, 3G, 4G test? Because if we test him in all positions, then we're really not worried about what position he welds in. He's qualified to weld all grooves. And in this scenario, he's qualified to weld in all true fillet joints. And this table is taken, this table 2 out of Appendix W. And we list this now because pipe nozzles right now, even though there are nozzles on a tank car, like Mike said, the nozzle is part of the tank, but Appendix W doesn't have pipe welding requirements in it right now. That's all been put together by the task force. It's been submitted to the tank car committee. So right now we're waiting for that to get approved, but eventually all the pipe welding requirements that's in D15-1, very similar, would be transitioned across to Appendix W. And then this is right out of AWS D15-1, very similar table, but as you can see, the bottom sections get into all the pipe welding requirements. And again, that eventually will be in Appendix W once it gets approved. And just to kind of zoom in on the plate test, so we take a 2G, 3G, 4G test. We have all for grooves, all for fillets. And then it also gives us all fillets on pipes. So that's in the code right now that you're allowed, as long as you take a 2G, 3G, 4G, you'd be qualified to weld, similar socket welds on brakes for on different parts. So I'm not going to really get into this, but this is kind of, if you go into either one of the codes, they're going to show you this table, and this is the position requirements. So if I give a welder just a 1G test, then I have to worry about going back to this section and going to flat up around the top, and then I would have to say, okay, well, if I incline more than 15 degrees, now I'm considered vertical, and then they have the rotational axis. And I like putting this in to show people because it really is kind of confusing. And this is if you sit down and break it out, you could figure it out. But this is exactly the reason that it's very customary to give a welder a 3-position test. This table goes away. I don't have to worry about it anymore because now my welders are certified in all positions, and I don't have to worry about my position limitation. Similar with F numbers, Mike talked about F numbers earlier. This is kind of the table that breaks down what the different F numbers are. And so like a 4F number would be, if you look at the section, a very common electrode we use is like 7018, which would be a 4F. And this just breaks out the different F numbers, and the next slides will show you a little bit better. So like 7018, which is a shielded metal arc, so like stick welding process. So the 70 is 70,000 tensile, 1's all position, 8 is low hydrogen. That would be an F4 filler metal. And then like 309L, which is commonly used to weld carbon to stainless, it's an F5 filler metal. So if I qualify my welder on carbon steel 7018, he's not qualified to weld 309 because the F number is higher, which is kind of the exact opposite if I go to flux core, because flux core is an F6 filler metal, even if it's FCAW E71T1. So 7 is 70,000 tensile, 1's all position, and a tubular electrode, and it's an F6. And then if I take a weld test on E71T1, since 309L, which is again what you use it commonly for welding stainless to carbon, or if you use 308 LT1, it's an F6. So you don't have to qualify welders on stainless with as long as the F number is the same. So in welding operator qualification, we showed you some tests earlier. And this is just kind of breaking out the different tests a welder would have to take, face bends, root bends, or if I'm going to do 2 side bends. And then that's a typical welder qualification sheet, which kind of breaks out. And what we really do is we list the actual requirements on the left side, what was actually done in the test. And then the right side gives me what parameters. So I took a 2G, 3G, 4G, and it lists everything I'm qualified. So it kind of breaks out, this is what I tested on, but this is what I'm qualified to weld. And it gives you your different ranges of thickness. And then period of effectiveness. So if I test a welder, how long is he certified? Well, you're basically certified indefinitely as long as 2 criteria are met. He has to use a welding process within a 6-month period, has to be documented, and then there's no specific reason to question his ability. If he's putting down good welds, his welds should be inspected every day. So if they're being inspected, there's no reason to question. And then, like I said, the 6 months is with each process. So if he welds with stick or SMAW, that gives him that, but he also has to weld flux core or gas metal arc weld. So that's basically the end of our presentation. We can open it up to some questions.
Okay, thank you, gentlemen. Yes, and now it is time for you to ask your questions. You can simply type a question into the question pane on the GoToWebinar sidebar, and it will come through, and we'll get to as many as we can in the time allowed. We ran a little bit long today, but we'll get to as many as we can, and we'll follow up with those that we don't get to. But to start off, gentlemen, a question came in: Are we required to qualify welders for Appendix W using TC128 material?
No, we're not. There is no requirement to use TC128 material to qualify a welder. A welder can use any ferrous material to qualify for welding. That's really the only limitation with regard to materials. I think a common mistake that's made is interpreting the essential variable table in Appendix W. There's a listing of essential variables that's comprehensive in text form, but there's also specific essential variables listed in the tables, and that's really what we all have to pay attention to with regard to either procedure qualification or performance. What's listed in the table, and just because it's listed in the comprehensive text does not make it an essential variable. So no, it is not required to use TC128.
Okay, thank you. And another one, earlier in the presentation, you mentioned that jacket welding would fall under AWS D15.1 specifications, but there was some talk about jacket welding going to fall into activity code B24. Have you heard if moving jacket welding to that activity code will change what specification welding will fall under the AAR or AWS specifications?
The D15.1 specification will still cover jacket welding. However, my understanding is, and it's just a theory at this point. We haven't seen anything finalized, but there's going to be a demonstration of jacket welding possibly required in Appendix D when the final version of that is released and approved. But it'll still be covered by D15.1.
Okay, and one more out there today before we wrap up. What is required for a fillet weld performance qualification test per AWS 15.1?
So fillet weld, for actually a fillet weld, you're required to do a brake test. Then, which is really common that they look at the code and they understand they have to do a brake test. But what they miss is they're also required to do a macro edge. So you're required, as Mike showed you the slides earlier about actually cross-sectioning apart, buffing it out, and actually hitting it with an acid. And what you're basically verifying is that you have adequate penetration in both legs of the weld to make sure the welder is producing a quality weld.
All right. Well, that marks the end of the Q&A today. We thank everybody for joining us. A reminder that a replay will be available late this week or early next week, and an email will be sent out to you once that is ready. Please don't hesitate to follow up with Steve or myself or any of us if you need anything related to today's content. Thank you to both of these fine gentlemen for joining us, and thanks so much to everyone for attending. I hope you have a fantastic day and a fantastic week. This concludes our webinar.